So, good evening, friends. Today is the second day of the workshop, and there are many candidates who joined today. So, for them, we are having the recordings for first day. So, yesterday we covered the basic definition of PLS, but these definitions are very important. Today, we are going to discuss the assumptions of PLS. So, whenever we are analyzing our data in PLS, so we have to examine many assumptions. So, the major assumptions you can see the assumptions of normality, internal consistency, reliability, validity, common method biasness, then multicollinearity. So all the things we will cover today. So these are the session topics which we are going to discuss. So all the topics we are going to cover in much detail. So let's go one by one. So first thing which we should know, and believe me, this is very important topic, normality. And many people ignore this concept. I have seen in some of the foreign cases, it is almost mandatory to report your normality. Why this is important? Because we assume that the population is always normally distributed. And if you want to apply the conclusions of the sample survey on the population, your sample should also be normally distributed. This property is known as statistical inference. So what is the meaning of statistical inference? That whatever conclusions we are drawing from the results, statistical analysis, that should also be applicable on the population. Like for example, whenever you are tasting something, suppose you are preparing a dish in the home, if you take a spoon to test the dish, so whatever conclusion you are drawing after tasting the spoon, the conclusion is applicable on the whole dish. So same concept we should have in the analysis. So that's why one of the condition that should be fulfilled is normal distribution. Another thing is that we normally divide the analytics into two parts, parametric and non-parametric. And the all parametric test like t-test, ANOVA test, regression test, correlation test, all these are parametric tests. So they have one of the major assumption that your data is normally distributed. So even PLS can be applicable of non-normal data, but we always require that the data should be normally distributed. If your sample size is more than 100, more than 50 even, so data should be normal. And the problem is that why data should not be normal? The question is that why data should not be normal. So I'm telling you some basic things, because if you are using 5-point scale, the data will be getting like this. So this frequency is highest when your data is neutral. So you can see in a 5-point scale, the normality only comes when you are having the maximum number of 3 answers. Which kind of response? Neutral responses. It is one of the problem which most of the scholars are facing. Actually, in practical, when you collect the data in 1 to 5 scale, your data normally getting is like this. So it is a skewed data, right? So sometimes it is not normal. So it is a very common problem that we don't have the normality in the data, and because of this reason, the scholars are facing a problem. So for this, I suggest you to use 7-point scale. At least 7-point scale is having the better normality. Okay, so there are two types of normality. One is univariate normality. Univariate means the normal distribution of a single variable. And multivariate normality means normal distribution of all variables taken together. So normal distribution. See, the normal distribution is measured like this, seems like this, a bell shaped. So the normality is measured by two things. One is the skewness and second is the kurtosis. Like if you have this kind of data, this is called skewed data. And kurtosis means you may have data like this, like this. So in this case, we are having symmetry, but height is different. For example, if somebody is having a height of 5'10", so you can say he is normal. If somebody is having a height of 4 feet, you say that the height is very less. If it is 7 feet, you say the height is very high. So these cases are called abnormal heights. This is a normal height. So this is known as kurtosis. So kurtosis is talking about the height of the distribution, and skewness is talking about the symmetry of the distribution. If data is not symmetric like this, so this problem is coming because of skewness. So I hope you you understand the meaning of skewness and kurtosis. Now, what the book says about this skewness and kurtosis, I am showing you the one of the paragraph which I taken from the book by Ringel, and this is the citation you can do. The name of the book is A Premier on PLS, page number 54. So they are talking about the distribution, data distribution. So in this paragraph, they are saying that one is the number which you can take. Like for example, this plus 1 and the minus 1. So I'm telling you the conclusion. What is the conclusion? The conclusion is that if the skewness and kurtosis are more than 1, it means the distribution is away from normal. And if skewness and kurtosis is less than 1, it means data is near to the normal. So they are comparing the skewness and kurtosis with plus minus 1, and ignore the sign, just 1. So we are having a simple conclusion. Whenever the skewness and kurtosis of a variable is less than 1, it is assumed to be normal distributed. So distribution is normal. So this is the condition that you have to prove, that the skewness and kurtosis is less than 1 of my variable. So this is the desired condition for any of the technique. And the same thing is also said by the Black and Hare book. So many people I have seen, they give the reference of Hare ETL, that skewness and kurtosis should be less than 1. So this is one reference, and it is the reference of a book which I gave you. Ideally, this is ideal. It should be 0, but it is just an ideal. It is not possible. Skewness and kurtosis 0 is not possible. I have not seen in any data set where skewness and kurtosis is 0. If it is less than 0.5, it is excellent. Excellent. It means whatever test you will apply, it will always come as a normal distribution. But most of us are dealing with the questionnaire data, where we are measuring in the scale of 1 to 5. In that case, skewness and kurtosis less than 1 or less than 1 is required. If you have skewness and kurtosis more than 1, then there is a problem. Why problem? In most of the papers, I have not seen that they are talking about the distribution. But whenever you are presenting for a thesis, they may ask you the normal distribution, or many reviewers may ask you about the normal distribution, that have you checked your normal distribution. So this is the one assumption which you should know. And if you're not dealing with the interval scale data, if you're having a ratio data, you can go for Kolmogorov-Ismentrov test or the Jarque-Bera test. But those tests are only applicable on the ratio data. I never seen that these tests applicable on the interval scale data. So for a interval scale data, you need not to apply any test like Kolmogorov or a Jarque-Bera. You just check whether the skewness and kurtosis is less than 1 or not. So that condition you should remember in always, that the skewness and kurtosis should not be more than 1, because this condition will save you from many problems. I'm telling you, there are many problems which only a statistician can tell you. Like whenever the distribution is not normal, goodness of it is always a problem. So normal distribution data, the goodness of it always comes better. So this is one of the uh, thing you should always keep in mind. Second thing is that multivariate normality. Multivariate normality is like a three-dimensional bell-shaped object. You have seen the bell in the temples, right? The bell in the temple is a 3D object. So that is called multivariate normality. Multivariate normality is measured by Mardia coefficient of kurtosis, and in MO software we can measure the Mardia coefficient of kurtosis. This Mardia coefficient of kurtosis examine the multivariate normality. Now I have tried many papers and many books to find out, is there any standardized condition for multivariate normality? And frankly speaking, I have not found even a single book or a paper which is talking about this Mardia coefficient of kurtosis. But from my experience, what is the ideal condition? The ideal condition is that suppose your number of items is 50. So Mardia coefficient of kurtosis should be less than 50. If you have 30 items in the measurement scale, the Mardia coefficient of kurtosis should be less than 30. So these conditions we should have in our mind to fulfill. If you have normality in the data set, I am telling you that you will not face many problems which you can't imagine. So the conclusion is that if you are examining the normality of the variables, the skewness and kurtosis should be less than 1. And if you are running the MO software where Mardia coefficient of kurtosis is coming, it should be less than the number of variables. So if you take these two conditions, many problems will not come. So this is the quotation from the book where they are comparing with plus minus 1. The second part is internal consistency reliability. But before that, I just show in PLS how we can compare the normality. So I am opening the PLS software side by side. I also showing you how to check all these things. So this is PLS, and yesterday we take a data set, the perceived work quality. So we are measuring on that data itself. So this is the PLS software, and it is our exercise number 1. So the moment you click on the data, you can see that you are getting the skewness and kurtosis. So this is kurtosis and this is skewness. So except for the serial number, because the first variable is serial number, so skip that. All other values of skewness and kurtosis, you can you can see that most of them are less than 1. So even they are only touching the 1. So in this way, you can find out the skewness and kurtosis from PLS. And mean, median, minimum, maximum, standard deviation. So all the things are coming in first page when you click on the data set. So from here, you can see the skewness and kurtosis. Okay. Now the second concept is how to check the reliability. So there are 3 types of reliability. One is the test, retest reliability. Where one is second is the internal consistency reliability. Then we have the inter-rater reliability. So test, retest reliability is measured when you are dealing with a machine, like in computer science or in physics. So we are using the same machine again and again. So we want to check whether the machine is still working properly or not. So that is called test retest reliability. For example, if you are measuring your weight again and again, so we are expecting that it should come same. So that is called the test retest liability. But when we are testing, when we are collecting the data from questionnaire, so we are not asking the same person again and again. Rather, we are asking the many persons at one time, first time even. So in this case, when you are taking the data from the questionnaire, you have to measure the internal consistency reliability. And whenever you are writing a paper, mention that Cronbach alpha is used to measure the internal consistency reliability. Don't say only reliability. You can say it is the internal consistency reliability. So Cronbach alpha, the formula is given here. This is the formula for Cronbach alpha. And you may not believe that Cronbach alpha is almost compulsory to represent in the paper. Whenever you are collecting the data from the questionnaire, you have to calculate the Cronbach alpha for each factor, for each construct. Cronbach alpha is calculated for each construct. So I have seen that many scholars have confusion that can we calculate Cronbach alpha for each item? Answer is no. Can we calculate the Cronbach alpha for the complete scale? No. Only construct wise. Okay. So if you see this formula, the Cronbach alpha value depends upon two things. One is the n, and what is n? N is the number of items. And what is average correlation? R bar is average correlation. So if number of items are more in the construct, if they have very high correlations, then Cronbach alpha is found to be very high. So Cronbach alpha is depends upon two things: number of items, which is n, and average correlation between them, R. So in one of the problem that I am facing in many of the projects, somebody says that, sir, I have 15 items in a construct. 15 items in a construct, it means the Cronbach alpha will come 0.95 or 0.96, because high n will shoot up your Cronbach alpha. So that's why I always suggest that don't put many items in the study. Otherwise, your Cronbach alpha comes very high. And with this Cronbach alpha, your composite reliability and other measures will also come very high. So that is a problem. Another thing is that when they are highly correlated, the R is very highly correlated. When you have duplicate items in the construct, the correlation is very high. And your Cronbach alpha found to be more than 0.93. Why I'm writing 0.93? Because the moment your Cronbach alpha exceed 0.9 or even 0.93, this condition is called redundancy. So nobody want to see the Cronbach alpha more than 0.93. I'm telling you, they will put an objection on the values that why your Cronbach alpha is very, very high. So you are suffering from the redundancy problem. So that's why the Cronbach alpha is one of the indicator of the quality of the responses in the questionnaire. So always check what is the value of Cronbach alpha for each value, each construct. So I'm telling you from my experience, if you are not applying SEM, the Cronbach alpha should be greater than 0.7, and if you are applying SEM, Cronbach alpha value should be more than 0.85 and 0.9. So this range is the best range of the Cronbach alpha. If your Cronbach alpha is less than 0.5, then you have a problem in AVE. The AVE will be less than 0.5. So what is the conclusion? Is simple. Conclusion is very simple. The Cronbach alpha should come in the range of 0.85 to 9. This is the best range of Cronbach alpha. If you have the Cronbach alpha in this range, many problems again will be solved automatically. So, and I'm just demonstrating the how we calculate Cronbach alpha. Suppose there are three variables: variable 1, variable 2, variable 3. Variable 1, variable 2, variable 3. The main diagonal is always 1. In correlation, the main diagonal is always 1, which means variable 1 and variable 1 are having 100% correlation, like this. So we can find out the Cronbach alpha value by this formula. First of all, we calculate the average correlation, like 0.6 plus 0.8 plus 0.7 divided by 3. So this is the average correlation. So first of all, we calculate average correlation. Average correlation is 0.7. And how many items are there? 3. 1, 2, 3. So 3 multiplied by 0.7, 1 plus and minus 1, which is 3 minus 1 multiplied by R bar. So this is the formula for calculating the Cronbach alpha. And in this way, we can find out the Cronbach alpha. So let me show you how we can calculate the Cronbach alpha. So in this data set, if you go to a model, so this is the model. If you double click on it, you can see the model. And to see model clearly, you just press on -1, this part. The model you can see very clearly. Okay. Now there are 5 constructs in this model, 1, 2, 3, 4, 5. And I want to analyze the Cronbach alpha for each. So what should we do? What should I do? So I go to the calculate. I go to the calculate. Consistent PLS algorithm. So I'm going to run consistent PLS algorithm. This is for assumption testing only. And just start calculation. And you can go for construct reliability. So the first value you are getting is Cronbach alpha. So you can see this is the value of Cronbach alpha. And the ideal range of Cronbach alpha is 0.8 to 0.85 to 0.9. So we have the Cronbach alpha in this range. It means our data is not having any problem. So this is the point we should remember with respect to the Cronbach alpha. So I think we are having clarity on the reliability analysis. Now we are moving to the next. So in books, I'm telling you, when I see the books, all the books are saying that the Cronbach alpha is more than 0.7. So 0.7 is the statutory limit. You can say that it is a bookish requirement. So there are two things. One is the bookish requirement, and second is the statistician requirement. So the book requirement of Cronbach alpha is 0.7, but I'm telling you, for a statistician, the requirement is between 0.8 and 0. These are the secrets that I'm sharing with you. So